Good afternoon, Namaskar. I, Kriti Vadhera, would like to welcome all the teachers, learners, educators, students to CIET NCERT's live phone program. And you're watching us live on PM eVIDYA's channel number 12. This session will be for 12th standard students. Physics is the subject which we are going to discuss next 1 hour for you. And the expert who is joining us today for this particular session, I would like to introduce Shri Rahul Chatterjee ji. He is joining us from Shillong Jail Road Boys School, Meghalaya. He is assistant lecturer there. We welcome you for today's live interaction program, Mr. Chatterjee.
Thank you.
And before we start with today's program here, viewers, I would like to remind you with a few details here that if you want to ask any question to our expert, then you may dial on our toll-free number to tell us. Number would be 8800440559. If you wish to watch the live streaming of this program, then you may kindly log into our official YouTube channel by the name of NCERT Official, and there also in the live chat box you may send all your suggestions and questions to us. One more medium to contact us: kindly mail all your suggestions and questions to dth.class12@ciet.nic.in. So these are the various mediums to contact us and send all your suggestions and questions to us. So let's begin with today's physics session. I would like to welcome you again, Mr. Chatterjee. What all topic we are going to discuss today in this particular session today?
Well, as you can see, the title of today's talk is the Rutherford's nuclear model of the atom. And this is a really very important topic as far as the class 12 syllabus is concerned. Okay. And not only that, as far as the learning of science is concerned, and as we progress from simple ideas to more and more complex ideas, Rutherford's model plays a pivotal role in making a major jump from what we knew to what we accept today. And so this is a really important topic, both in terms of the history of science, the development of science, as well as our syllabus and the examination. So the topics that the way the lesson is going to progress is first, we will look at the history leading up to the landmark alpha scattering experiment. Then we're going to look at the experimental setup itself. Then we will look at the observations when they performed the experiment. What observations did they take? What did they see? And then what conclusions did they draw from these observations? And therefore, what new proposals did they make? And finally, the successes and limitations of the new model. So these are the headings under which we will cover our lesson. We will look at our lesson today. So if we begin, should I?
Yes, you may proceed with your session and presentation, Mr. Chatterjee. All our viewers are waiting for it.
Thank you so much. So let's start off with the historical development. I always say nothing happens before its time. So the time was ripe for someone to do this experiment. And Rutherford designed the experiment, but his students, Geiger and Marsden, they were the ones who actually performed the experiment, and we will see their names more in this lesson. So what was the environment, what was the knowledge that we had before this experiment? Well, in 1897, J.J. Thomson had done some experiments on the electric discharge tube, and he put some gases under low pressure in these discharge tubes and passed current, high voltage current through them. And through these experiments, what he found was whatever material he may be putting inside, whatever gas he may be putting inside the tube, they always produced a negatively charged particle. And these negatively charged particles were identical across elements. So even though he put different gases, he always found the negative charges to be identical. What he measured was what we call the specific charge, the Q by M, the charge by mass, and he found that to be identical. So therefore, the particle was identical. And then, therefore, if an atom has negative charges and the atom overall is neutral, then it means that there must be positive charges as well of equal number. So Thomson therefore concluded that the atom must have equal number of positive and negative charges. Fine. But the question is, how are these positive and negative charges distributed? How are they arranged? So he gave a very simple model. उन्होंने कहा कि in a sea of positive charges, the negative charges are interspersed. Imagine you have a watermelon, and in the whole watermelon, the seeds are distributed. So the same way, of course, he called it the plum pudding model. Plum pudding is a dessert we have, a sweet dish we have at the end of the food, and in that, at the top, currants and cherries are just distributed. So he said the model is something similar. You have the positive and negative charges evenly distributed, and so the atom overall is neutral, right? And by the 19th century, early 19th century, we already knew of the line structure of the spectrum of atoms. This has already been seen particularly by Balmer, and Balmer did some good work on coming up with some empirical formula for the line structure of hydrogen atom. Now, these were things we knew, but the problem was these were not fitting into Thomson's model of the atom. So we needed to study more. So it is this environment under which Rutherford performed the experiment. And so this is the setup of the experiment, and this picture, as you can all recognize, is straight from your textbook, the NCERT textbook. And this is a schematic diagram. So you can see an alpha source over here. Let me take the laser pointer. Then perhaps it'd be better. Yeah. So this is the alpha source. From here, alpha particles shoot out, and they're allowed to enter through only a very narrow gap. The rest of it is the detector. Not really the detector. It is the zinc sulfide screen, and I'll tell you how we detect it. And then these alpha particles go and are incident on this gold foil, and this gold foil is really, really thin. It is just 2.1 into 10 to the power minus 7 meter. So it's like 1/10 of a micron. A micron is 10 to the power minus 6. This is even thinner than a micron. Okay, and as you can see, after these particles, the alpha particles, strike the gold foil, they scatter. They scatter in different directions, and we'll see why they scatter and what happens as a result. And what was the alpha source he had taken? He had taken 83 bismuth, and 83 bismuth gives off 5.5 MeV alpha particles. Okay, 5.5 MeV, which is pretty fast. The kinetic energy of the alpha particles is pretty high. 5.5 MeV is pretty strong. Okay. Let's look at the detailed diagram of this now. So here's the source of alpha particles. Now here are some lead bricks, so that alpha particles which are coming out, they really come out in all directions, but we don't want it in all directions. We want them to come out in a fine pencil beam, and so these lead bricks are put over there with a small opening. So this is the angular spread of the alpha particles that we can have if the opening of the lead bricks, the open path is this much. So this is the kind of spread we may have. And let's imagine that we have a gold atom over here, because he had taken a gold foil target. So let's say there is a gold atom over here. So some of the alpha particles will go above it, some will go below it, some will come and strike it directly, and then as a result, we will have these scattering. And what he noticed was, here is the zinc sulfide screen, and when these scattered particles come and strike the zinc sulfide screen, you see scintillations. Now what are scintillations? S-C-I-N-T-I-L-L-A-T-I-O-N-S. Scintillations. Scintillations are tiny specks of light. Very, very tiny specks of light. Now normally you wouldn't be able to see it. With a naked eye you would not be able to see scintillations. And that is why we need a microscope. So it is with a microscope that we can see these tiny dots of light, little flashes of light. They don't stay too long. So you got to pay attention and you got to see these scintillations. And so what they did was, they placed this microscope at a particular angle, which is called the scattering angle, at an angle theta from the original direction of the alpha particles. So, and then they measured, or rather they counted the number of alpha particles, let's say in 1 minute. Okay, the number of scintillations, the number of little specks of light that came out per minute, let's say. Okay, then change the angle a little, come to a different place and do the same thing, and do the same thing, and do the same thing, and keep on doing the same thing for as long as you can rotate this microscope. And only what they did was they really rotated it all around almost 180 degrees. Okay, and so what they found as a result of this was that, as you can see over here, about 1 in 8,000 is reflected backwards. It's coming backwards. Are there any that are really reflected at 180 degrees back, retracing their own path? Yes, much fewer than 1 in 8,000, but there are. That's very important to us. Most of these particles simply go through straight and hit the target over here. I mean, hit the zinc sulfide screen over here. They just pass through. Okay, so let's see more of this. And what he did was, out of this experiment and out of these observations that he had, so he counted, he sat down, Geiger and Marsden, they sat down and counted these particles, let's say per minute, okay, depending on the scattering angle. So they plotted a graph of the number of particles versus the scattering angle. And here is the plot that I'm going to show you first with solid dots on the data from the experiment. So this is the data from the experiment. So you see, when the scattering angle is very small, जब scattering angle छोटी है, तब बहुत सारे particles यहाँ दिख रहे हैं being scattered. छोटे angle में, छोटे scattering angle में बहुत सारे particles, almost 10 to the power 7 particles we are seeing. As scattering angle is increasing, number of particles कम होते जा रहे हैं. तो जब scattering angle is large, 140 degrees, 150 degrees, 160 degrees, almost 180 degrees, then we have very few particles. But it is not zero. That is the important thing. It is not zero. There are a few particles. It could be less than 100, but there are. That is important to us. Even if there is one particle being scattered at 180 degrees, it is important to us. But what we are noticing is that ज़्यादातर particles कम scattering angle में scattered हो रहा है. Either they are going straight through, zero, okay, or very small, very 1 degree, 2 degree scattering, just a little bent. Now, this is directly from the experiment. Now, what they also did was, they did a theoretical model. They imagined a theoretical model in which they assumed that all the positive charge is concentrated at the center and electrons are going around that nucleus. And now if I fire alpha particles, then what would happen? How would the particles be scattered? So this is a completely theoretical model. Okay, so they did the calculations for it, taking gold, because atomic number of gold is 79. So taking all that, they did the calculations. And what kind of a graph did they get with the theoretical model? Here it is. Look at that. They match perfectly. That is an absolute beauty. Theoretical model has matched perfectly with the experimental results, which means we will be very safe to say that our model of the atom is one in which the central core is positively charged and most of the mass and charge is in the central core and the electrons go around it. We will be very safe to say that because our theoretical model and our experimental results have matched perfectly. So here in this animation, this is what I'm showing you, that all these particles, they start off and there are very few which turn back, but there are some. but most of them are simply going forward. They're simply going forward, right? So that is what the experiment showed. Now, here, let me spend some time on this and explain a little more. Just let's make it a little more detailed. So if we have, let me start with these, yeah, okay. So if there is a particle which is very far away from the nucleus, then it is not deviated at all, it just goes straight. Whereas if there is a particle slightly nearer, then it does feel some of the repulsion, because alpha particles are positive, the nucleus is positive, and so there is some repulsion and it bends. If it is still closer, the bending is even more, and if it is still closer, then the bending is even more. And look at this one, there's a sharp bend, and this one, the next one, is very close, and there's a right angle scattering, 90-degree scattering. But there are very few which have greater than 90-degree scattering. So here was one very close to the nucleus, but not hitting the nucleus directly, and there was a large angle scattering greater than 90 degrees. But if there is a particle which is headed for the nucleus absolutely head on, straight, then what happens to it? It goes straight and rebounds back, right? So this particular one that goes straight and rebounds back is very useful to us. We will use this in the next kind of calculation that we're going to do, right? So let's move on. So these were the observations. So from these observations, let's write down the observations first. So what did we observe? We observed that most of the alpha particles pass straight through the gold foil or experience very small angle scattering. And that's what you can see here in this animation as well. Most of the particles are simply coming through on the other side of the gold foil. There are very few of the particles reflected behind the gold foil, right? Secondly, very few alpha particles scatter through large angles that is greater than 90 degrees. That's what I just said. Thirdly, very rarely do we see alpha particle rebound, that is scatter through an angle of 180 degrees, but we do. Very, very rarely we see that, but it's not zero. We do see a few of them. The fact that we see very few of them is very important to us. So, if these were our observations, then what are the conclusions we draw from these observations? Number one, the entire positive charge of the atom must be concentrated in the tiny central core of the atom. Why do we say that? Why do we say that the entire charge must be concentrated over here? Look, if it was Thomson's model, that all the positive and negative charges are spread out equally, then we cannot explain such a large angle scattering. We cannot explain 90-degree scattering. Even this kind of a scattering cannot be explained with single positive charges. A single proton does not have so much repulsion on an alpha particle of 5.5 MeV kinetic energy that it would be able to give it this kind of repulsion, this kind of trajectory change. It's not possible. The calculations just don't permit that. You must have much, much greater charge here in the nucleus so that the alpha particle can get deflected, can get scattered by such a large angle. And that is why this first conclusion that the most of the charge must be concentrated at the center, right? And the fact that most of the charges simply go through on the other side without getting deflected at all, like this one and this one at the two ends. We'll see what that means. It means that there's a lot of space between two atoms. So we said the entire positive charge of the atom must be concentrated in a tiny central core of the atom, and that central core is given the name nucleus. And if we have all the the positive charges in one place, and an atom has to be neutral, then we must have negative charges. Then where are the negative charges? Then this model says, well, then the negative charges go around the central nucleus. Okay? So If it is to go around the central nucleus, it's going in a circular path. And for anything that goes in a circular path, we need a centripetal force. So what is providing the centripetal force? The Coulomb attraction. There is a positive, negative attraction between the electron and the positive nucleus. So that Coulomb attraction is providing the centripetal force. And thirdly, as I said, there is a lot of empty space between the two atoms, because between any two atoms, because we see a lot of the atoms simply go through straight. That means it is simply not affected by anything. The ones that are very close to the nucleus, they deflect. The ones slightly away don't get deflected or slightly deflected and simply go through, right? So which means there is a lot of empty space between the atoms. Now, if that is the picture, let's look at a little calculation that we want to do, the distance of closest approach. Now you see, you recall that particular alpha particle that was coming head on. So if it is coming head on, let's say this is the nucleus, and here is an alpha particle coming head on. So it starts off with 5.5 MeV kinetic energy. As it approaches the positive nucleus, it will slow down, slow down, slow down, slow down, stop, and then it will get rebounded back because of the repulsion. It will never be able to come and collide, never be able to come and touch really. So when we say they collide, we don't mean they touch, okay? So these are elastic collisions where they come very close up to a certain distance, they cannot come up anymore because of the repulsion, and then move back. So what is happening in this interaction? What is happening is the entire kinetic energy from the start is decreasing as it comes forward because the velocity is decreasing, and then the potential energy, the electric potential energy is increasing, 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 and at the distance of closest approach, electric potential energy is maximum and the kinetic energy is 0, right? All kinetic energy has been converted into potential energy, electric potential energy, and then it gets converted back into kinetic energy when it rebounds back. But at that point, at the point of closest approach, at that point, the original kinetic energy, 5.5 MeV, has all been converted into potential energy, right? That is very important to us. So we'll look at that. So to do this calculation, we make a few assumptions. So first assumption is that the nucleus and the nucleus is very heavy. So when the alpha particle comes, the nucleus really doesn't move. Okay, so there is no apparent movement, there is no movement of the nucleus, and we are safe to do that actually, particularly for gold. It is very safe to do that because mass is 79 and alpha particle is just 4. So pretty safe to do that. So these are meaningful assumptions. The alpha particle and the nucleus can be regarded as point particles without any dimension. They are really tiny, so point particles, good enough assumption again. And the scattering is due to elastic collision between alpha particle and nucleus. So elastic collision, if you recall from your knowledge in class 11, that means kinetic energy gets conserved and no kinetic energy is lost in the process. Okay, so with that, with those assumptions, so let's look at the mathematics behind this. So we are talking about this particular one, this one marked with the red. This is the one we are interested in, not in the other ones. Okay, the one that makes a head-on collision, goes up to a certain distance and then rebounds back. So for that one, as I described, on account of Coulomb repulsion, it will go nearer, slow down, stop, and then come back. And so this nearest distance we are calling R0. Okay. So at R0, the entire kinetic energy has been converted to electrical potential energy. So let's see now what the values are we working with. So the charge on the alpha particle is plus 2e. Alpha particle is doubly positive. It has 2 protons and 2 neutrons. So forget the neutrons now. The neutrons don't bother us now. We are only bothered about the plus 2 protons. And the charge on the nucleus is Ze, where Z is the atomic number. In our case, it is gold. So for gold, Z for gold is 79. So when we really do the calculation, we will put Z as 79 over there. Now, electric potential at a distance, we know the formula is 1 by 4 pi epsilon naught Q by R. And that is what we've done, 1 by 4 pi epsilon naught. The charge Q is Z times E over R naught is the closest distance, the distance of closest approach. And so if that is the potential, what is the potential energy? Potential energy is potential into charge. So potential into charge. So 1 by 4 pi epsilon naught ZE by R naught times the charge 2E. So that's the potential energy. So that's the potential energy. Fine. Now this potential energy at the distance of closest approach must be equal to the original kinetic energy. The original kinetic energy, half mv square. So we can equate these two things now. And so we have half mv square is equal to 2ze square by 4 pi epsilon naught R naught. Put in the values now. First, okay, we want to find the distance of closest approach. And so let's write the equation for R naught. And this is the structure of the equation for R naught. And now, if we find the value of R naught and we call that the size of the nucleus, obviously our size of the nucleus is going to be much bigger than what it actually is, because as we said just now, that the alpha particle never actually goes and touches the nucleus. It goes near it, but it cannot go and touch it because of the repulsion. So we're going to get a size much bigger than what it actually is. Okay, but so be it. Let us do the calculation for R naught. And if we put in the values, then this 9 into 10 to the power 9 comes from this 1 by 4 pi epsilon naught. 1 by 4 is 9 into 10 to the power 9, we know that. Z is 79, and then the 2 is this 2, and then you have a E into E, which is E squared, so that's the charge on the proton, and so 1.6 10 to the power minus 19 squared, so because it's E squared. And the half mv square, when you convert it into joule, into SI unit, you get 8.8 10 to the power minus 13, right? And so if you do this calculation, then this is what you land up with, that R naught is 4.13 10 to the power minus 14 meter, which is 41.3 Fermi. Now what is good about this is that we did get the Fermi correct, 10 to the power minus 15, we got that bit correct. So order of magnitude is absolutely correct, even though this 41.3 is a little too big, and naturally we understand the reason for that. Because the particle, the alpha particle never goes and touches the nucleus. So we got it a little bigger. But at least order of magnitude, we got it correct. Now see, before I go to the Rutherford's atomic model, the size of the nucleus is 10 to the power minus 15. That's what we got here. And size of the entire atom is 10 to the power minus 10, which we can calculate from kinetic theory. So there is a 10 to the power 5 difference between the size of the atom and size of the nucleus, which is remarkable, which is really remarkable. And even without doing any other calculation, you can understand the amount of empty space that is there between the nucleus and the first orbit of the electron. There's a lot of empty space. And there's a famous quote by Richard Feynman. Richard Feynman said, there's a lot of empty space down there. It's a famous quotation, and that is what he was referring to. That down inside the atom, you have a lot of empty space. Okay, so all these calculations, these experiments, the observations, the conclusions, and therefore, Thomson's model needs to be thrown out, because we find that Thomson's model cannot explain what we saw in this experiment, and so a new model must be proposed, right? So the Rutherford's atomic model. What does it say? It says every atom consists of a central core where the entire mass of the atom and all its positive charge is concentrated, and this central core is called the nucleus. And this is for the first time that the name nucleus was given, because before that the concept of nucleus wasn't there, the need for it wasn't there, right? Because in Thomson's model everything is distributed. Secondly, the size of the nucleus is of the order of 10 to the power minus 15 meter, which is much smaller in comparison to the size of the atom, which is of the size of 10 to the power minus 10 meter. And I mentioned that just a while back. Thirdly, the atomic nucleus is surrounded by electrons equal in number to the protons, making a neutral atom. So the model says, this is something new also, that Rutherford's model says that the electrons go around the nucleus, central nucleus, in circular orbits. He actually mentioned circular orbits, okay? In circular orbits, and the centripetal force required for that is provided by the Coulomb attraction between the negative electrons and the positive nucleus, right? So this was the model given by Rutherford. And it had some successes and some failures. So let's look at the successes first. Okay, it just gave me a signal that my internet connection is wavering. So that's why I just kept quiet for some time. I hope you can hear me now. Right, let's look at the...
But you are properly audible and visible to us, Mr. Chatterjee. I guess there's no issue.
Oh, okay.
Your screen is also visible and you're totally audible to us.
Great, that's great. So, what are the successes of Rutherford's theory? First, it could explain the large angle scattering of alpha particles through thin foils. This is really, really important. Being able to explain why alpha particles should deviate from their path and go away in different directions through large angles is really, really important. And also the fact that very few of them have scattering angles greater than 90 degrees. That tells us that the nucleus must be very, very small. That very few particles have an opportunity to have or to be very close to the nucleus because it is so small. If it were bigger, then more particles, more alpha particles could come and strike it. But that's not what is happening. That means the nucleus is very small, so most of the particles miss it, very few collide with it, and some are deflected because of the repulsion, right? So really successful theory. It could explain the large angle scattering. It justified the classification of elements in the periodic table according to atomic number and not atomic weight. Remember, initially when we made a periodic table, it was by atomic weight, and then things didn't fall in place. Ultimately, we had to change that periodic table and see the structure of the atomic periodic table.
Mr. Chatterjee, before you move further, I would like to tell you here that if we are getting a question here on our official YouTube streaming, which is happening now, by one of our viewer by the name of Ronak. He wants to ask you why there is not attraction force between electrons and alpha particles.
Oh, absolutely. Fantastic question, Ronak. Thank you so much for that question. I just missed that point, and thank you for reminding me to tell you this. Absolutely important to say this, and it's going to be helpful for everybody else also. Yeah, certainly there is interaction, that means attraction between alpha particles and the negative electrons. Absolutely, you cannot deny that. But why don't we consider it here? Okay. Let me give the answer first and then elaborate. We don't consider it here because the interaction is much, much weaker. Okay. Now, why should it be weaker? And why can we ignore it? It's like this. See, most of the time in physics, there are multiple phenomena happening, right? Say during the day, when temperature increases, we say, okay, the temperature rose by so much. And in a separate chapter, we teach you about increase in pressure and increase in humidity, again in a different chapter. But during the day, all three of them are happening at the same time. There is increase, decrease in temperature, there is increase, decrease in pressure, there is increase, decrease in humidity. So all those things are happening at the same time, right? And so in physics, there are a number of phenomena where multiple things happen at the same time. But we ignore some and take some. Which do we ignore? The ones that are negligible. The effects are negligible. Which do we take? The effects which stand out, right? So here we find that electrons in this model are going around as single individuals. Electrons are going around as single individuals in orbits around the nucleus, right? So an interaction between an alpha particle and an electron is an interaction between a single electron and the alpha particle. That interaction is very weak. the amount of deviation, the amount of attraction that this can bring is very little in comparison to the deviation that the entire positive charge concentrated at one point can bring to the alpha particle. And that is what we get to see also in the experimental results. And so ignoring the effect of the negative charges of the atom is justified. Okay, Ronak, I hope I've answered your question. If you still have queries, do put another question in, and I'll try and answer that.
Yes, absolutely.
So
you explained it so beautifully, and you have elaborated in a way, and I would request all our viewers who are watching us live, you may send more questions as our expert is there to answer them back. You may proceed with the presentation, Mr. Chatterjee.
Thank you.
Meanwhile,
so,
if I'll be getting any questions, I'll be telling you.
Sure, thank you so much. So it justified, as I was saying, that remember our old periodic table was according to atomic weight and not atomic number. I mean, we didn't even know that there was something like atomic number. We didn't even know that, the nucleus is made of the atom, has a nucleus, and there are protons inside that, and there are equal number of electrons going around. We didn't know these things. And so the first obvious information that comes to us is the total mass of an atom. The total mass of the atom is atomic weight. And that's how we arranged the periodic table, and then things didn't work out. The octave rule does not work out that way. And finally, when we arranged it according to atomic number, that's when we saw more design in the whole thing, that more regularity in the pattern of reactions, and that's how our modern periodic table is designed. So it justified that very much. But what were the limitations of the Rutherford's model? It couldn't explain everything. The first thing it couldn't explain is that classically, you see, from classical electrodynamics, we know that whenever an electron is accelerated, you make it shoot out in a direction, change its direction, say oscillate it. Oscillation is a kind of acceleration, right? Because the direction is changing, the velocity is changing. So whenever we do that, it gives off electromagnetic waves. So we know classically that whenever you accelerate an electron, it will give off electromagnetic waves. And in class 11, you have learned that an electron going around in a circular path, even if it is going in with equal speed, even if the speed does not change, still it is accelerated motion because the direction is changing, right? Because we say acceleration is rate of change of velocity, and velocity is a vector. It has two qualities about it. Velocity has magnitude and it has direction. So you could change either one of them to change, or both, but at least one of them to change the velocity, and therefore call it acceleration. So in the case of uniform circular motion, that's what we taught you in class 11. In the case of uniform circular motion, what is uniform? Uniform is the angular speed. The angular speed is uniform, but it is accelerated motion because the direction is changing all the time. It is not moving in a straight line. So it is accelerated motion. And therefore, by classical electrodynamics, this electron, which is going in a circular path, must lose energy and ultimately fall into the nucleus. And if it falls into the nucleus, the atom will get destroyed. Atom by atom in the universe, this should have already happened by now, and therefore the universe shouldn't have existed. But obviously that does not happen. So something is wrong in this model. This model has not been able to explain something. So here I have an animation for you. So there you are, the electron spiraling into the nucleus, right? And that is one thing. Moreover, if the electron actually spirals this way and goes towards the nucleus, then it should be continuously losing energy, and we should be able to detect that radiation. And we do detect radiation from atoms, but the radiation that we detect from atoms is line spectra. They come in specific lines. But what we should expect from this model, from this theory, is that it should be continuous spectra, because it is continuously falling into the nucleus, and ultimately it is making smaller and smaller circles and ultimately falling into the nucleus. So if I could just play that once more, there you are. So since it is a continuous path, its energy is decreasing continuously, so we should get a continuous spectrum. But that's not what we see. We see line spectrum. Gas after gas, atom after atom, element after element, we have seen that everything, when you take them in individuals, as individuals, not as a cluster, not as solid condensed matter, then we see that they have line spectra like this. So the top one is for neon, neon's famous red light, and when you go out we say the neon lights, and this is that famous red light that we see from neon signs. This is for hydrogen. The bottom one is for hydrogen, and the famous H-alpha line, which we see all over the universe, and as a signature that hydrogen exists all over the universe. This is a signature H-alpha line for hydrogen. But these are all line spectra. Continuous spectrum is like the one on the right hand side, and we don't see this for atoms. So this is something the model could not explain. And so these were the failures of the model. But then this was a very good start. This was an extremely good start. And from this point onward, Rutherford's model came to be established as the model. But because it had certain failures, Niels Bohr took it up. And then Niels Bohr took it one step further and explained why electrons in certain special orbits will not lose energy. If there are some special orbits satisfying some special conditions, well, that is a completely new topic, but I'm just giving you an introduction to that topic because this leads to that topic, right? And that is why I'm not going to do Bohr's model of the atom today. That's a full class again. So I'm just giving you an introduction to that and how this leads to that. So here is the limitation or the failures of Rutherford's model. And this model predicts that the electron should fall into the nucleus, but we know it doesn't. So Bohr came up and gave the explanation for that. And Bohr said that there are some special orbits in which electrons, if they revolve around the nucleus, then they do not fall into the nucleus. They will stay there. These are stable orbits. These are stationary orbits, right? And there's a condition, he said, which must be fulfilled. He said the total angular momentum must be an integral multiple of h by 2 pi, where h is Planck's constant, right? And we can see that when we really do that particular model. So with Bohr's model, what we get is specific orbits are allowed orbits. So we have one orbit which is allowed. Outside that, we have another orbit which is allowed. But between those two orbits, nothing is allowed. So there is an empty space. If you put an electron in that empty space between the two orbits, it will fall into the inner one. It cannot stay there where it is not allowed to stay. Okay? And then outside the second orbit, there is a third possibility of another orbit, and so on. And it is exactly like I've drawn over here. So there is a possibility of one orbit over here, and then there's a possibility of a second orbit over there. But in between, there is no possibility. So Bohr said that here is 1 h by 2 pi. Here it is 2 h by 2 pi. And then if there is a third orbit, it would be 3 h by 2 pi. The total angular momentum would be an integral multiple of h by 2 pi. And that's when you get a stationary orbit, right? And then Bohr's model was able to explain line spectra, particularly for hydrogen. Okay, because Bohr's model is a very, very simplistic model, so it could explain it pretty precisely for the simplest atom, hydrogen. Okay, so I think that covers the topic that we had at hand today, and Yeah. So if you have questions, I'm there to answer. How much time do we have? We have about 10 minutes. So
yes, we
good
have
time
another
to
10
answer
minutes,
the
and I
question.
would urge our you viewers here who are watching us live on official YouTube streaming. Viewers, if you have any questions, then you may please write in the comment box. I can see many viewers are watching us live here. So likewise, Ronak asked, you also can ask and send your questions to our official YouTube streaming on NCRT Official. We would be more than happy to address all your questions here with our expert.
Absolutely. That's right.
Yes, Mr. Chatterjee, for another 10 minutes, I would like to ask you that anything else you would like to tell our 12th standard students which they have to keep in mind while studying this chapter?
Okay. There are a few things that we find in answer scripts, okay, that we want students to be very familiar with. One is the conversion from MeV to Joule. And what is the connection? What is MEV? MEV stands for million electron volts or mega electron volts, right? So what is the conversion ratio between MEV and Joule? Well, 1 EV, 1 electron volt, not 1 million electron volt. 1 EV, 1 electron volt is 1.6 into 10 to the power minus 19 Joule. Okay? So 1 MeV would be 6 times 10 to the power 6 times smaller than that, right? Then there's another question that I have been asked many times while teaching, that okay, I understand that this is the model, that everything tells us that this is the model. Rutherford's model is the model, that everything is the 99.99% of the mass and charge is concentrated at the center. I can understand that. But suppose Thomson's model was the model, then what differences would we see in the observations? How would our observations be different? This is something that I've been asked many times. And it's a good question, because they're trying to probe how, when you change the basic realities, what output changes, how the output changes. And so the answer, in fact, I have already given while discussing this topic. And I said that if the charges are distributed, positive and negative charges are distributed uniformly, then you have one positive charge to repel this alpha particle, because you don't have all of them concentrated at one point. You have one single positive charge to repel that alpha particle, and so naturally the repulsion will be very strong, very weak, and so the angle of deflection, the scattering angle, will be very small. You will never have a situation where you have large angles of scattering which are greater than 90 degrees. It's impossible. The calculations show it, because we know the mass of the alpha particle. It is 4, 2 protons and 2 neutrons, pro. And there you have, if you have the Thomson's model, then you have single particles. So you have 1 proton, single proton. A single proton trying to deflect a particle which has 2 positive charges, but mass is 4 times. And it's impossible. I mean, even common sense tells us that, oh, that's impossible. And so we would not see such large angle scattering, number one. Number two, if electrons and protons, electrons and protons are interspersed, then just like there would be repulsion between protons and alpha particles, there would be attraction between electrons and alpha particles as well. And this time, both the interactions would be equal, and the possibility of multiple interactions, multiple scattering would be there. That possibility would be there, which is not there in the case of Rutherford's model. In the case of Rutherford's model, multiple scattering possibility is not there, because the electrons are so far out between the nucleus and the first orbit. There is so much of empty space that the alpha particles can simply go through that space and not being affected by the electrons going around in orbits. They can simply go through that space between the nucleus and the first orbit. So there is no question of multiple scattering. The only scattering that can happen is due to the positive nucleus. Right? So that is one question that has often been asked. If there are no more questions on the...
We still have another 5 minutes, Mr. Chatterjee, to sum up our today's session.
Yeah, okay. If you want me to sum it up, then well, I'll put it this way. There are very rare occasions in the history of science, in the development of science, in the progress of science, that things have happened before their time, or the leap is huge. One such leap was, I'm quoting examples from what is in your syllabus. There are many other examples outside your syllabus. So one such leap within your syllabus, it was something that came before its time, was the Van de Graaff generator. If you recall your chapter on electrostatics, the Van de Graaff generator came before its time. I mean, before the Van de Graaff generator, the charges that could be built were in maybe 100 volts, a few hundred volts, and then the Van de Graaff generator came, and one step we jumped into millions of volts, no thousands. One step, one shot we jumped. So that kind of is something that comes before its time. Normally, there are kind of step improvements, very measured step improvements, and you can see the progress of science that way. That was one. The other one is when we study the effect of magnetic field on charged particles. There, when we have the cyclotron, that was a huge thing. A simple cyclotron, the capability of it to accelerate particles is so high that it can reach relativistic values. It can reach beyond 85–90% of the speed of light, and so relativistic effects take over. And for such a simple instrument to be able to do that was remarkable. And see, these are some examples that have come before its time. But here, in our situation, you see, there was this need. It didn't come before its time. There was this need to probe into it because the existing model, the Thomson model, was not being able to explain what we were observing. And so someone had to probe it. And by the way, Rutherford was a student of J.J. Thomson. And so the student actually did better than the teacher. And then again, Geiger and Muller, who actually performed the experiment, are again students of Rutherford. Okay, so this is a really wonderful combination, collaboration rather, so if you look at the development, you look at the stages, and this is something I always tell my student: please keep the big picture in your head. Do not study physics as a topic. Please look at the big picture. Why have we included this particular topic in the syllabus and the one before it and the one after it? Because there is a logical sequence between these. There is a development in the thought process. There is a development in the technology, or there is a development in our knowledge. And that you must be able to appreciate when you study physics. Topic by topic, chapter by chapter, be able to connect them. It's sad that we teach physics as, watertight chapters. That's not how nature is. Nature blends between all the aspects. And we must be able to understand that. We must be able to connect one chapter with the other, electricity with magnetism, heat and thermodynamics with something else, and everything, because everything happens together. And we must see all of this at the same time, not as watertight compartments, right? And so this particular model, Rutherford's model, really was the crying need of the hour, and explained a few things, gave a particularly new model, could not explain a few things, but it was certainly a step increase, a step improvement in our understanding.
Right.
And then came the next step, the Bohr's model of the atom, which was another step improvement. And that's how and Bohr's model was not the end, because then there were changes to that. Sommerfeld's model was a further improvement on Bohr's model.
Right. So this was from physics session today, viewers, and you can see how beautifully our expert has explained each and every minute detail of this particular chapter. And Mr. Chatterjee has also explained to all of you that physics is a subject which should not be just confined to this curriculum based activities or just the textbooks, as he said, that you have to think beyond the textbooks to explore physics. I really thank you, Mr. Chatterjee, for joining us today for this wonderful session.
Thank you. My pleasure. Absolute pleasure. Thank you all so much for asking me, and I hope the children from the country benefit from this. I'm always available.
Absolutely. I'm sure that all of our viewers must have gained a lot out of today's session. So that was physics session, viewers. I would request you to get yourself vaccinated. Keep maintaining social distancing. That's how we can prevent ourselves from this deadly COVID-19 virus, and remain connected to PM eVIDYA to watch NCERT's resource material. Thank you. Namaskar.